In this tutorial, we will solve some problems related to polynomial functions. In particular, we'll reference the fundamental theorem of algebra. The fundamental theorem of algebra states that a polynomial function of degree n has exactly n zeros. A zero, or a root, is a value of the domain that results in the function being zero. A function can have real zeros and/or complex zeros. A real zero is an x-intercept of the graphed function. A complex zero will be in the form a plus bi, where I is defined as the square root of -1. To find or verify the zeros of a polynomial function, we will set f of x equal to 0. We'll factor the polynomial and then apply the zero product property and then solve for x. So in our example here, we are given the zeros of a polynomial function as -3, -1, 2, and 5. So these are real numbers, right? So there are 4 places where this curve will intersect the x-axis. The degree of this polynomial function is 4. So what we want to do is we can apply the zero product property in reverse, and each of those zeros are the x values which will result in the function being 0. So we can write x minus that first root times x minus the second root times x minus the third root times x minus the fourth root, and that will be our function f of x. Now we can simplify this. And here we can take the first 2 binomials and multiply them together, and the second 2 binomials and multiply them together. And if I wanted to, I could multiply these 2 trinomials together using the box strategy. Let's write the first trinomial across the top and the second one along the side, and we'll multiply the terms that result in the cells. So x squared times x squared plus 4x plus 3 results in this piece. Now we'll multiply the -7x by the values along the top. Then we'll multiply 10 times the values along the top. And now we will put all of these terms together, looking for like terms. And we will write this function as x to the 4th minus 3x to the 3rd power minus 15x squared plus 19x plus 30. Now what's nice is we can use graphing utilities such as Desmos or a graphing calculator. We can enter this equation into the graphing utility to double check and verify that in fact the zeros are what we claim they would be. So we'll graph this function, and we're looking at the zeros, the places where the curve crosses the x-axis. They are respectively -3, -1, 2, and 5. So it checks out. We'll do one more example where the real zeros and the degree are given. In this example, -1 is a real zero with multiplicity 1. 3 is a real zero with multiplicity 2. This function has a degree of 3. So we will apply the zero product property in reverse, remembering that 0 will be the result of x minus -1 times x minus 3 times x minus 3. Notice the x minus 3 is there twice because of the multiplicity of 2. So f of x then is equal to x plus 1 times x minus 3 times x minus 3. We can multiply the first 2 binomials together, and now multiply that trinomial by the binomial using our box strategy. Being careful as we multiply, we get x cubed minus 2x squared minus 3x. And in the bottom row, we'll get negative 3x squared plus 6x, and then 9. Here are our like terms. Our resulting polynomial function is f of x equals x to the third power minus 5x squared plus 3x plus 9. And we are going to graph this using a graphing calculator to verify that everything looks correct. So when we graph this function, we see that there is a root or a 0 at negative 1 with multiplicity 1. That's why it crosses right through the x-axis at negative 1. But notice the root, which is 3, we call this a double root because the function touches or bounces at that point, proving that the multiplicity is 2 at x equals 3.